Now it's time for Benjamin to do a little experimenting. He has a crank generator, and he has a light bulb connected to it. Go ahead, Ben. Crank whichever way you want. A little faster. Okay. What happens when you crank it?
The light bulb lights up.
All right. Now, Ben, does it matter which direction you're cranking it? No, it doesn't? So if you crank it either way, it'll work? Yes? No? That's one way. And I go the other way? It looks like it does. No matter which way you crank it, it works. Crank it slow till it just lights. A little bit brighter. Okay, now crank it fast. So what's the relationship between how fast you're cranking and how much light we see?
Faster you go, the brighter it gets.
That's true.
Wow, in hindsight, those circuits flying by, super distracting. So, I will have more on the new homework posted with this bit of notes, just typed out. I'm actually going to kind of breeze through electromotive force and internal resistance and focus on these circuit rules and problems with those circuit rules. So, electromotive force, if you ever see this, think of it as another way of saying voltage in the ideal perfect case, where nothing takes away from the total voltage of a circuit. Now, back when we were looking at, and you can read through that yourself, back when we were looking at the power generation station at Cornell, I said they couldn't have too much water flowing through the generator. Why? Because of this little R thing right here. Now, it's one thing to have a circuit where you pop in a resistor or a light bulb that you know is going to cause resistance and slow down the circuit. It's another thing if, as the circuit is functioning, it actually slows itself down, and that's what happens when you have too much running through that generator. Too much water going through the generator will actually make the turbines that create electricity out of the flowing water, it'll make those turbines heat up. As the turbines heat up, it makes the resistivity, that function of a metal that allows electricity to flow, it actually takes that resistivity and it jacks it up. It actually makes it harder for current to flow when a circuit gets hotter. So internal resistance multiplied by the current running through the circuit actually takes away from the total voltage the circuit can create. So, for example, if this equation is to help me figure out how much voltage I'm getting out of my flashlight, well, I have a 9-volt battery in the flashlight. The 9 volts goes right here. It is my electromotive source. As I turn the flashlight on and current runs through it, current will run through the flashlight bulb, and it will actually heat the bulb up. As the bulb heats up, it creates its own source of slowdown, and it takes away from that total 9 volts. So let's say, because of the current running through and the internal resistance created, it takes away half a volt. So I start with 9 volts, this takes away half a volt. If I were to measure the voltage of the actual circuit, I'd get 8.5 volts. That's just the reality of how circuits work, but we're not going to focus on that. Today is more about the rules of series and parallel.
Ben, what I want you to do is I want you to crank it at a pace where I can see that the light bulb is lit and it stays lit the same way. Go ahead. Good job. That's exactly what I need. Now, what happens, do you think, if we try and hook up 2 light bulbs and you crank it the exact same way? Will it still light?
Maybe?
Well, let's find out. Okay, Ben, try cranking these 2 lights now. Now, to get them to light up the same amount, can you crank the same, or do you have to crank more to light these ones?
Crank more.
Show me. So you have to crank more to get those things to light the same way the other one lit. What do we call it when we have these 2 lights and there's only one way for electricity to get from one side to the other?
We talked about series and parallel with capacitors. The term series will mean the same thing. The term parallel will mean the same thing. Let's forget about the math for right now, because the math is going to be about different things here. What you do need to know is that if I have this switch and I flick the switch, I'm going to have current running from this battery through each one of these light bulbs. The light bulbs are going to be like resistors, and it will look like this. to go from one side of the battery to the other, it has to go through each one of those light bulbs, each one of those resistors, which means that is a series circuit. Okay? So, series means one path for current to flow, and if I were to unplug one of these lights or cut here or turn the switch off, suddenly nothing works. So one break in the line, everything stops. Take out one light bulb, everything stops. Should you wire a house like that? Think about it. More on that later. The math, the rules for these particular kinds of puzzle, pretty straightforward with series. The current, the total current in a series circuit is equal to current every place else. So, if I put an ammeter in here and measure the current running through the circuit, I get the same thing if I put it here, here, or here. It doesn't matter where, current is the same every place. Voltage is not the same. Voltage is going to be additive. So if I have 3 resistors there and I have a voltage across each resistor, I have to add those voltages up. So let's say the voltage across this light bulb is 3 volts. The voltage across this light bulb is 3 volts. The voltage across that light bulb is 3 volts. What is the total voltage according to the rules? 3 volts plus 3 volts plus 3 volts gives me my 9-volt battery. That's the idea, at least. Okay? So, voltage adds up. Don't get that confused with the EMF equation I gave you before. Again, that's just the reality. I wanted to say it was a reality, but this is us treating some ideal cases. Resistance, same rule, kind of, as voltage. Resistance adds up. So let's say each one of these is a 1 ohm resistor. 1 ohm plus 1 ohm plus 1 ohm, that means 3 ohms total resistance in the circuit. Alright, series is pretty simple that way. Here's our rules, okay? Current's the same everywhere. Voltage across everything adds up to the total voltage, and to get the total resistance, you add up the value of each resistor. Now on to the more interesting circuits.
Now we have a different setup. Now we have a light bulb here, so the generator powers this light bulb, and the generator goes right back, okay? That wire goes right back to the generator. But we made like a second loop right here with another light bulb. It's hooked together kind of like a ladder. Go ahead and crank him, Ben. When he gets those going, he can light up both the light bulbs just a little bit easier than he could light up the other two the other way. When we have these two, or 2 light bulbs or 2 resistors hooked up in such a way that electricity has a choice, it could either go through this one or it could go through this one, we call that
parallel. Now parallel is more interesting because honestly it's more useful. You have a battery here or a power source, turn on the power source, flip the switch, and you're suddenly going to be powering each of these. Now how is it parallel? Well, there's not one path anymore, there's more than one path. There's path A, B, and C. So if I flip the switch, I actually power up all 3 through different paths. And my rules have to kind of make sense of that, okay? So our circuitry rules apply, and now we have a little bit different set of rules. So take a look at this. Current, it's no longer the same every place. In a parallel circuit where there's more than one avenue for current to flow, your total current is going to be a sum of each current. So the current through A plus through B plus through C makes the total current measured here or here. That's just how it is. So current adds up. Voltage, however, voltage is identical every place. Because we have multiple paths, all powered by the same battery, they're all getting the exact same push. It's not divided up at all. So if this is a 9-volt battery, that means there's 9 volts across this one, 9 volts across that one, and 9 volts across this one. Simple, straightforward. So voltage is the same everywhere in parallel, but current adds up. And now we come down to resistance. This is one that looks a lot like those capacitance rules. It's the one that you really need to make sure you have your parentheses in the right place when you're doing these problems. It says 1 over the total resistance. So 1 over the total resistance, that's what equivalent resistance means, is equal to 1 over each resistor added together. So 1 over the inverse of each resistor. So the sum of these inverses gives you the inverse of the total resistance. Again, we can shoot that through that real quick. So let's apply the rules. Again, I'm trying to go through this kind of fast. Pause at any time. I would say take these down as little bits of an example to help you with the homework. I have a circuit in front of me. How many paths do you see from one side of the power source to the other? From here to here, I see one path. One path. This is a series circuit. Okay? Find the equivalent resistance of a series circuit. What were those rules? Hopefully you wrote them down. But the rule for a series circuit is that your resistance must add up. So the total resistance in the circuit is going to be the same as 2 plus 4 plus 6. So we've got 12 ohms total resistance. Alright, so my total resistance is 12 ohms. And I do that just by applying that rule. And there you go. What is the total current in the circuit? Well, I don't have anything to look at. I know that the rule says that I could find the current here. It'd be the same as current here, here, and here. So current's the same everywhere, but that doesn't give me a number. What could I use if I know voltage and resistance to find current? If you're thinking Ohm's law, you're right. That simulation you did before that showed the relationship between current, voltage, and resistance is exactly what we would need in a case like this. And current is going to be equal to voltage divided by resistance. So the current in this case is going to be 48 volts divided by 12 ohms. That gives me my 4 amps total current. Okay, so I apply the rules and I figure out something about my circuit. Again, it's like a little logic puzzle, but the rules for the circuits help us work our way through. That one's pretty straightforward. Now for one that's a little more interesting. And that's going to be a parallel circuit. Again, multiple paths, so as soon as that switch is flipped, I'm powering all 3 paths independently. So A1, A2, and A3, they're all getting slightly different currents through them. The only thing that's going to be the same from one place to another is voltage. So now that I know that I have a parallel circuit, let's take a look. What kind of information do I need to find? How about find the voltage across each one of those resistors? Well, I did just say the rule. And the rule is, if I know my total voltage, I will know the voltage everywhere. So if this is 48 volts down here on the power source, that means there's going to be 48 volts there, and 48 volts there, and 48 volts there. There's my basic rules laid out. So I got to keep that in mind. I know resistance here is 6 ohms. I know voltage is 48. I know resistance here is 4. I know the voltage is 48. I know the resistance here is 2 ohms. And 48 is going to be my voltage. I could figure out more information from that. Specifically, if I wanted to, I could find the current in each resistor if I just take the voltage across that resistor and its individual resistance. For example, if I have 48 volts across here and it's 2 ohms, that means the actual current is going to be 24 amps. If I have 48 volts and 4 ohms, my actual current's 12. If I have 48 volts and 6 ohms, I've got 8 amps of current. And if I were to combine them, 24 plus that, 36 plus that, I've got 44 amps of current through this entire circuit. Alright, there we go. So current through each one, added together because this is a parallel circuit, gives me 44 amps of current. Now if I move further forward, I could even find the equivalent resistance of the circuit. There's a couple different ways. One is the really complex one where it's 1 over the total resistance is equal to 1 over the first resistor plus 1 over the second resistor plus 1 over the third. There are 2 ways of doing it, so I will choose the easy way. Since I already know that there are 48 volts of current total, 48 volts total in this circuit, and I know the total current is 44 amps from that previous part, I'm just going to make my life easier and use Ohm's law. Total 48 volts divided by 44 amps should give me 1.1 ohms of resistance. Now notice 1.1 ohms is also less than any of those resistors. But that's okay because this is a parallel circuit. And the parallel circuit has this as its rule, where the total resistance is the sum of the inverses of all the resistors, which means my total should be smaller than any resistor. So whether you do it this way, where 1 over the total is equal to 1 over 2 ohms plus 1 over 4 ohms plus 1 over 6 ohms, or you use Ohm's law, just rearranged, you'll get the same answer of 1.1 ohms of total resistance. And that's how you use the rules in really quick format. I'm going to post homework, and I will also post a session where I can help you with the homework if you have questions, and we're going to be posting a lab simulation on building circuits and using these rules. Thank you very much for paying attention.